All right, hello. Thanks for coming, and big kudos to the organizers for bringing the community together. So my name is Pavel, and I'm going to talk about blockchain implemented in Go. And actually, I want first to kind of align the expectation because today when I was kind of finalizing the slides, I realized that probably you would think that we will actually start building blockchain from scratch here right now. No, unfortunately it's not the case. I will just talk about what I do. So a couple of words about me. Currently, I work at a company called Guardtime. It's an Estonian company, and I am originally myself from Estonia. I relocated to the Netherlands 5 years ago. But the company itself, I joined, it's also 5 years ago in 2019. It was founded in 2006 and started implementing blockchains already then, before it became the hype. So if you remember, Bitcoin appeared in 2008 or 9, etc. And before that, no one actually knew what blockchains are. But again, the company was working in the field of cryptography and data security and using blockchains in order to provide cryptographic timestamping to build supply chains and other services. So like it was not related to cryptocurrency. Only 3 years ago, we kind of also decided that we have enough experience to start because we saw a lot of drawbacks in the blockchain systems, platforms, and we decided to build our own. And this is what I will talk about today. I also worked at Zero Return before, and back in the days spent about 10 years in academia at Taltech, which is Tallinn University of Technology. All right, so just quickly, I'm sure you know what the blockchains are. So it's a distributed ledger, which allows putting data and then keep it immutable, right? And usually the data in the form of transactions is put into the blocks. Then the blocks are certified, and then the next block is linked to the previous one. So you get this chain of blocks which are cryptographically linked and cannot be changed. And if something is changed in between, then it's very easily verifiable. There are a lot of problems with the blockchain, and I think nowadays, like we hear a lot about like blockchains, cryptocurrencies, and whatnot, but there is still no massive adoption. And one of the reasons is scalability, because if we take modern cryptocurrency blockchains, then their settlement time is 10 minutes or more. You cannot just go and go to the supermarket and pay with your bitcoins, because no one will actually wait 10 minutes in the queue while your payment gets the confirmations. So in this platform, the main thing that we wanted to address was scalability. And there are multiple ways to achieve scaling, and there are some blockchains, Solana, for example, that just try to scale vertically, adding more computing power into like a single server machine. And there is another approach to actually scale horizontally. Our implementation takes the second approach. So again, I have to bring you into the context of like why we are doing that. So before jumping into the Go implementation, I really have to explain like why there is a need for another layer 1 blockchain. And so if we take well-known blockchains such as Bitcoin, for example, if you know, Bitcoin is based on the UTXOs, which is an unspent transaction outputs. meaning that, for example, if you want to know your balance, you need to dig all the transactions that you have from the blocks, and then you will know your balance. And if you want to transfer some value, then you have like a transaction which takes multiple unspent transaction outputs from the older transactions, and then you build this a new transaction, and then part of it will go as an output to the recipient, and then maybe you want to return something to yourself, and that basically leads to a lot of branching and a lot of checks. So in order to prove that the transaction is valid, a lot of state has to be checked to validate the transaction. And in Ethereum, for example, Ethereum is an account-based blockchain where for each address there is a certain balance written, and then if you want to transfer something to another address, then each transaction has to touch at least two accounts. And again, since those systems are distributed, then yeah, it's not that easy, and basically it also requires a lot of state to be verified. And in our platform, what we propose is that we took an inspiration from the physical cash, where, for example, if I have a 10-euro bill and I want to pay someone, I just transfer my, I don't know, I'm not touching it, and it's, maybe I have some kind of auto switch of my slides. Anyway, so if I want to transfer my bill, I just give it to VJ, and that's it. It's one transaction, and we are just swapping the ownership of this bill, and we don't and this transaction is completely independent on all other bills that are existing in the system. It's just one ownership swap, and that's it. And for every bill in the system, if we want to transact, then there is the verification of each transaction is independent on all the rest, right? So with this approach, we can actually achieve massive scalability, because all the verification happens independently, and then each bill can have its own ledger, can have its own history. And there is a scientific paper where it was proven by professors that work in our team that this is the case, and this approach in terms of scalability is much better than the other approaches. So now we kind of get into the meat, and so in order to achieve this scalability, it's a distributed system which is also decomposed into various components. So we can have this blockchain, it has like a single state, but the state is distributed among many components that we call partitions, right? There is the root partition that kind of governs all the rest and certifies the block production of all other partitions, and and here we can have those partitions where we can have this native currency, which we call alpha, and then we can have a partition which only has fungible or non-fungible tokens, and then we can have a partition for user contracts, etc. And when users interact with the blockchain, their transactions go into those specific shards, and each shard can service, I don't know, thousands of transactions. And since we can, each shard can do this independently, because there is no inter-shard communication, and we can add those shards as much as we want, depending on the throughput, for example. Then we can basically scale linearly with like infinite amounts. So we just need to like buy more servers and deploy more validators. All right, so yeah, let's hurry up because we don't have a lot of time. So yeah, it's just another slide that shows that in Ethereum, in a state tree, you have to touch at least 2 nodes, and in Alphabill, every transaction just affects one node. And yeah, so the state, again, what? So we have units in the system which carry some kind of a value or can represent a fungible token, non-fungible token, like the monetary unit, etc. And it is represented as a node in the state tree. And then there are transactions which are being recorded into the blocks. And blocks are like certified and then stored. So you get the blockchain, but at a particular point of time, in the memory of the validator, there is a state tree that holds the most recent state of those units, right? And then, for example, if you shut down the node and then you spin it up again, then there are there are 2 options. Either you can replay all the blocks from the genesis to recreate the state tree, or actually we now have also the so-called the state file, so where we just dump the tree into the file, which leads to the very quick restart of the system. And yeah, for the state tree, we are using the AVL tree, which is a self-balancing tree with very quick lookups. All right, and yeah, as I said, since the state is decomposed, we can have like transactions being processed by multiple shards in parallel, and add as much shards as we want. Okay, so I hope I haven't lost you yet. So let's talk about some more details about the stack. So 3 years ago we started, and on the version with Go without generics, etc. So now we are trying to keep up with the most recent versions of Go, and use generics and all the latest stuff. And actually, so when I was kind of preparing the slide, I realized that in the system, most of the things, all those cryptographic proofs, Merkle trees, AVL trees, etc. So a lot of data structures we actually written ourselves, because this is pretty much how you operate in Go. You implement a lot of things yourself, and of course, we use more libraries than listed here, but most of the things we have implemented ourselves. For configuration in the command line interface, we use Viper and Cobra, and we used to have our own logger, but I think some recent versions of Go introduced the native logger, so we switched to that. For simplicity, we use the embedded storage BoltDB. And 1 year ago, when I was attending the Go meetup here in Rotterdam for the first time, there was also actually a talk about BoltDB. I think it was a mail service. And so I was also very curious about the wrapper that was written to do some queries for the BoltDB. But we actually, I looked at it, but we actually wrote our own wrapper around BoltDB, which was much more simpler than the one that was shown. Anyway, for the networking, we use the libp2p, which is a great library. If you want to build a distributed system, then this is the way to go. offers service discovery, and then you can build your own like protocols on top of this library, and it like builds and maintains and updates the routing tables between the nodes. So yeah, it's a very powerful tool. We started off with protobufs and gRPC, and then realized that it doesn't fit our needs because of like multiple reasons. And one of them was that we wanted to have consistent hashing, and serialized protobufs didn't provide this. So we switched to CBOR, which is a concise binary object representation. I will have a slide later on this. And also, yeah, decided since we were ditching protobufs, we got rid of the gRPC as well and switched it to the JSON RPC, even though our payloads, so we are offering JSON RPC for the client side. So the communication between the validators and like the components of the system, they speak with our own protocols over libp2p. But for the clients, we offer JSON RPC endpoints. But in those payloads in JSON, we actually encode our data structures in CBOR. So basically, it's just byte arrays going back and forth. Yeah, and we also have observability. So we use those Grafana and Elastic and all that to track the system. And integration tests using the test containers. Does anyone know test containers? Okay, 3 people, yeah? Okay, more, nice. All right, yeah, I was a big fan when I was, so yeah, that was actually my first project in Go that I've been doing for 3 years. Before that, I was Java programmer for more than 20 years. And test containers is a really nice thing that came initially out of the Java ecosystem. All right, so I already said that the main building block of the platform are the units, and units have the owner, right? And owner is like not a like surname of a person or something. It's actually a function. We call it a predicate, because if you want to manipulate the unit, say it's a non-fungible token, you have a nice picture of your I don't know, ape or a cat, or actually NFT can be something useful like a university diploma, which is tokenized, etc. So NFTs are actually very nice concept that we use in real world applications, not for speculating on some on some images. And if you want to do something with the unit, you must prove that you are the owner, right? And basically this script, the ownership script is a predicate, and a predicate, you know, from computer science is a function that evaluates to a Boolean value, true or false, right? And if you are able to provide a proof to satisfy this function, a predicate, and it will evaluate to true, you will have the authorization to actually do something with the unit, say transfer it to someone else, or update the NFT data or whatnot. And I will show you in the next slide how it works. And of course, there are transactions that manipulate the units. And I mentioned partitions. So basically, one partition implements a transaction system, because different partitions can have different units, right? Token partition can have fungible, non-fungible tokens. And then money partition can have those bills or like money units. And all these units require different transactions. And we aggregate those transactions into transaction systems and say that, okay, a partition is an instance of a transaction system. And then it can be further decomposed into shards, and each shard will have multiple validators. So, all right, finally, I can show you some data structures. Yeah, so the transaction order is something that has a payload, and the payload has a bunch of fields like network ID and then unit ID. Unit ID is a identifier of a unit to actually find it in the state tree. And of course, your transaction must go into a correct partition ID. And network ID is basically you have a mainnet, testnet, devnet, whatnot. So basically make sure that your transaction is sent into a proper place. And then there are multiple types of transactions, which is just, we used to have those types of strings, which was very readable for our QA was very happy. But now we decided that, okay, we can actually have them just as integers. So we made QA less happy, but they're getting used to it. And then, yeah, there is a field called attributes. So this is a basically generic transaction that is the same for all transaction systems. And the difference comes only in the type and in the set of attributes that is being sent with a particular transaction order. So here, maybe again, it's not very readable, but the auth proof, the authorization proof is actually this argument that needs to go and satisfy this ownership predicate. So if this fails, then this transaction is rejected. If this argument is able to satisfy the predicate, then the transaction itself goes into the processing. And yeah, basically raw CBOR is just an alias for a byte array because, with some additional methods attached to it. Yeah, since Go is kind of limited in terms of inheritance and so on, that's why here we actually have to include the serialized fields, and depending, for example, on the type, transaction systems knows how to deserialize the attributes to the correct type, and then continue processing the transaction. And yeah, also like this field without a name actually tells this CBOR serializer how to actually serialize those data structures. So I think in Go that usually JSON serializers use the tags, JSON tags for each field. With the CBOR serializer, you can just say that, okay, you want all the fields to be encoded as this CBOR array, and that's it. You don't have to do anything else. You don't have to define for each field independently. All right. So, and if we talk about transaction attributes, then, how long has it been off? Yeah, so almost there. Yeah. And again, just an example. So in this money partition, we have several transaction orders, transaction types, and then an example of a transfer of a money bill from one owner to another is that you specify the value, and then you present. So here you will have this authentication proof, and then this attributes goes here, and then once this transaction is applied, the new function, the new predicate will be written into the state tree for this unit that will already contain this lock script for the new owner, and a counter which is like a unit counts how many transactions it actually took, because it's done in order to avoid the replay attacks, right? So that someone cannot just take an existing transaction from older block and then replay it on top of the latest state. So again, that is a small part of the system, but I wanted to show you that, yeah, so actually developing blockchain is not that easy. And we have a massive specification, the yellow paper of the system, which is, I think, almost 200 pages now, which is really mathematical. But here, I can, yeah, since I don't have a laser, I will try to point. So the client creates a transaction, signs it, and sends it into the validator, right? And there is a transaction buffer, and the processing of transaction actually happens sequentially. So the transaction buffer is something that accumulates those transactions, and then through the channel sends those transactions into the coroutine, which just has a loop which waits on the new transactions in order to process them. And the transaction processing happens within a round, and the round is about 1 second. So if one round is able to process like as many transactions as it can until the timeout, then those transactions will be put into the proposal. And again, since it's a distributed system, then every round there is a leader validator and multiple followers. And the leader actually puts those transactions together into a so-called block proposal and sends this block proposal into the root chain for the certification. And also it sends it to other validators to verify. And then other validators check this proposal, also send the proposal into the root chain. And if everyone is satisfied, there is this consensus where everyone say that, okay, I calculated the root hash of the state tree to be this value, and then root chain checks that, okay, if all those hashes are the same, or there is, I mean, the consensus doesn't have to be 100%, but if the majority is of those hashes is equal, then it can certify the block and send back the proof that will certify this. And this is how it goes. And of course, if some node was down and then it has to catch up, etc., there are replication protocols, and then, I mean, yeah, it's there are a lot of things. But in a nutshell, this is how the validator actually works, and I hope I was able to kind of give more or less understandable explanation. All right, I wanted to, yeah, I don't know, maybe you were wondering what the predicates are and how can you lock the unit. And I thought, okay, maybe I can just briefly show you how it's actually done. So when we started working on this project, we took some inspiration from Bitcoin actually, and also implemented our own stack-based opcode language, a form of the domain-specific language, if you wish. So we implemented our language like ourselves, defined a certain amount of those operations, and each operation was manipulating the stack. The stack was also written ourselves, which is again very simple data structure. It's like an array of byte arrays, and yeah, like the regular stack implementation that you usually would implement in your job interview. So yeah, there is this function itself, and there is a predicate argument, which means that this is this proof that must satisfy the predicate. And the most used predicate in the system is basically locking a unit to a public key hash, right? So I have a wallet, I have a key pair there, public key and private key, and for example, my unit is locked for my public key. That means that inside this unit data in the state tree, there is a script, which is a byte array, which looks like that, right? So you don't need to memorize it right now, but I have a simulation. And then the argument to unlock the script looks like this. So you need to provide a signature. A signature is that when a client creates a transaction, it hashes the transaction and then signs it with its private key, right? And then this small script is just a proof that this signature was signed with this with the key pair which had this public key, because in order to sign you need to have a private key, and in order to verify you need to have a public key, right? So here you provide this signature with a public key, and then if you can calculate the same hash that was signed and verify that it was actually signed with the same public key, private key, then everything should be good, right? So here I show you that first we execute this this argument script, and then the second will be executed this the predicate itself, right? So we push the signature to the stack, we push the public key to the stack, and then now we just sequentially process the predicate itself. So we duplicate the public key and we hash it, right? So this is our stack. There we hash it, and then we calculate the hash of the transaction that came, and then we check if those hashes P1 and P2 are equal. They are true. So equal just takes two elements from the stack and replaces with a Boolean if it's true or not. Verify just checks if the top element is true. If not, it fails. And then basically the check signature just takes, assumes there is a public key in the signature, and it checks one against each other. And if everything is good, it leaves true in the stack. And this condition was that if the top element from the stack is true and the rest of the stack is empty, then it's all good. We return and predicate is satisfied. Otherwise, we return an error, meaning that it's not satisfied and the transaction will be rejected. Yeah, simple as that. But we got rid of this stack-based language because it was kind of in the roadmap that we want to have the full programmability of our units. So we started looking at the WebAssembly. We actually did some analysis and we're looking at some other languages, but eventually we thought that okay, actually WebAssembly is a nice option because a lot of languages actually support compiling into WebAssembly, so you can have a predicate written in Rust or in Go, or I don't know, maybe in Java, etc., and then compile it into WebAssembly and then run it inside our blockchain. So yeah, so this is we have the kind of work. We have a working implementation right now, but it still needs polishing and a lot of things have to be done. And yeah, for that we had to fork the runtime for WebAssembly written in Go, because we had to add our own gas metering, because again we need to fortify our platform from infinite loops and from some other things that might come inside those transactions, and so we need to first of all have a deterministic fees for the transactions, so that we can calculate upfront what what the fee amount would be, and also like if it goes out of scope, then we can also terminate the execution of the transaction, etc. So yeah, that's quite a challenging thing, which is like still in progress. Okay, so again, when we talk about blockchains, right, there is a lot of cryptography involved around that, and when you have those like transactions, sometimes you need to present proofs either to some other transactions or maybe to clients or to other wallets that, okay, actually that transaction took place and that it is in the blockchain, and then how do you actually do it, right? And so usually when you hear a proof in the context of a blockchain, then yeah, it's some cryptographic data structure that allows you, to do something. And for example, since the transactions are recorded in the blocks, then we need to produce those transaction inclusion or execution proofs. And it is done using the index Merkle trees. And the Merkle tree is a pretty simple data structure where you have a tree and all transactions or all your things that you are interested in are in the leaves. And then you hash each node. And when you go from the leaf to the root, then at each step, you basically take the hashes of underlying nodes, hash them together, and then propagate those hashes upwards up to the root. So you end up with the root hash. And if you want to produce a proof that this transaction is actually in the block, this data structure allows you to create the proof by including the sibling hashes, like not the whole tree itself, because I mean the block can be large with a lot of transactions, but you only want to have a proof for your particular transaction, right? So say in this example, this is this transaction Y, and then yeah, you have a hash of this transaction. You want to make sure that it's in the block, and then this proof that is being generated only includes those sibling hashes, because yeah, I mean, if you have this hash, you don't need to know about these nodes, right? Because basically you only need to know this the path to the root from your transaction, and this is how you implement and calculate the proof on the Merkle trees. And again, we have many other proofs in the system. And for example, this unicity certificate is also another proof that certifies the block as a whole. Yeah. All right. I'm almost done. So a couple of words about the consensus, because again, multiple blockchains, like different blockchains have different consensus. And in our case, it's a deterministic finality. So Bitcoin, for example, uses the longest chain rule, and there are probabilistic convergence and some other consensus algorithms. And in our case, the deterministic finality actually allows us to reach the settlement of around 2 seconds for one block, right? So when you do some transaction, either payment or like any other transaction in the system, you actually pretty much have almost an instant finality. And so this consensus is based on the Byzantine fault tolerance. It's a well-known and well-studied topic in computer science, and yeah, it tolerates, in our case, like 1/3 of failures, meaning that some validators can be either malicious, or maybe they are down, or like something happened to them, etc. So the system will continue operating if there are at least 2/3 of validators online. Yeah. All right. So again, I wanted to speak about like elaborate on some things that we did and why, but I guess time is up. So yeah, just maybe focus on the last thing, the cyber encoding. So it actually is quite concise, and since we are using arrays instead of those maps, actually in our case we don't have those key names in our serialized cyber, so it's actually even more compact. But this is how it looks like, and we are also using like cyber tags that help us to allow identifying, just looking at the serialized data, what data structures are actually inside. Because even sometimes when you look at the JSON payload, you can kind of, and if you have similar data structures, then maybe you cannot say if it's that and this or that. But with cyber tags, you can actually achieve it. And yeah, so there's still, we are not yet in the mainnet. We have a testnet which was running. The latest version was running since April, and we will soon release a big update. But yeah, I mean, there's still much work to be done. Yeah, so we have we don't have like full-blown smart contracts yet, but again, with WebAssembly engine, we will be able to achieve this. We have a prototype of the Block Explorer, and also Java SDK and some other things. So yeah, it's for me personally, it's a very interesting and challenging project. Yeah, and I really like working on it. All right, so it's open source. You can, if you are interested, you can go and read the white paper or join the Discord channel and server, or go to GitHub. We actually split the main repo into multiple other repos. It was one point for convenience, and another was related to the licensing, because the validator licensed as a GPL, and then all the rest of the components we license as a project. So thanks for listening, and we have a pretty big team working on that, and it's fun. Thanks.